بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله. In this video, we will talk about the transient response of second order systems. Okay, we already finished the transient response of first order systems. When we say transient response analysis or the time domain analysis, we're talking about two types of problems. Either you have the system model, you have the equation of motion, or the transfer function of the system, and you want to draw the transient response, showing all these specifications. The other kind of problems you expect to see in this chapter is what if you don't know the model? You are in the field, you are in the lab, and you have a system, first order or second order, and you want to get the model. When I say get the model, get the transfer function and the equation of motion. And we are interested in that, finding the model to control it, to design a controller in order to keep everything under control. Okay, so these are the two types of problems. Either you have the model and you want to draw the transient response, or you have the transient response from an experiment, and then you want to find the model, derive the model. Okay, now we talked about already in the past lectures or videos, we talked about first order system. First order system are very simple. Okay, usually you have one kind of response. It's always going to be exponential. Okay, either growth or decaying. If you have a step input, it will be always a growth. Okay, as we did last time. And the only parameter that's important for first order systems is tau. Now for second order system, which is the talk of this video, all right, it's going to be more complicated. When I say it's more complicated, I mean there are more cases. Okay, when you want to draw the transient response for second order systems, there are more cases. Okay, it's more complicated. Okay, usually each case depending on what kind of damping, how much damping do you have in the system. Okay, so it's very different. Okay, so here today, what we're gonna do, we will talk about how to draw the transient response for second order systems. Okay, we will talk about 4 cases. Case number 1, what if you have a second order system without damping? Now when we say second order system, usually most of the systems that we know, second order is a mechanical system, if you remember. Okay, so there is zeta, there is damping. Okay, so the first case we will draw system without damper. Then the second case we will add a damping. Okay, so this is the case with underdamped. This is what we're going to do today. Critically damped, when the damping is equal to the critical damping, and overdamped when we add too much damping to the system. Okay, these are the cases that we're going to talk today. Later, inshallah, in the next lectures or videos, okay, we will talk about the opposite. What if you have the experimental results and you want to derive the model, find the equation of motion or the transfer function? And then after that, we will talk about the specifications. For second order system, there are more specifications. Okay, when you want to design a controller, what are the specifications? Okay, for the transient response that you are interested in. These are in the next videos. Okay, so today we're going to focus only on these. Okay, how to draw the transient response for a second order system. Okay, all right, let's start with case number 1, the easiest one. We have a second order system, mechanical system, without damper. Okay, without damper. So zeta here is equal to how much? Zeta will be equal to 0. Remember zeta. Zeta is the damping. How much damping do you have over the critical damping? So you have no damping, so zeta will be 0. Okay, this is the equation of motion of the system given. The model is given, with the initial conditions are also given. Okay, we did this example in chapter 3. We solve it. Okay, we derive the equation of motion in the standard form. This is the standard form. Okay, it will help us to draw the transient response, and we derive the solution step by step. Now you don't have to derive the solution again. Okay, why? Because the solution will be always the same for a second order system, depending on how much zeta do you have. I will show you what do I mean by that. All right, for this system, look at the solution. Okay, it's going to be always what? Sinusoidal. Okay, For a second order system, it will be always sinusoidal. This is the time domain. This is x of t, the solution. Now, how the solution will look like, it's going to be sinusoidal. How do I know that? From the solution. Is it for any mass and spring system? Yes, for any mass and spring system, it will be always the same, just different numbers. What are the different numbers? I will show you. So it's going to be sinusoidal with what? With the constant amplitude. Okay, so it's going to be cosine with constant amplitude. Okay, so you can see the amplitude is fixed. Okay, the amplitude is fixed. How much this maximum amplitude? You can see that from the solution. This is the maximum amplitude, R given. Okay, this is the R given. How much R? We got it from here, from the sine and cosine. If you remember, you can review this in chapter 3. Square root of the initial conditions, depending on the initial conditions, the parameter of cosine square plus the parameter of sine square. This is how we get R, okay? Here we're going to focus on how to draw the transient response only, okay? The solution, you can check that for proof. But it's going to be always the same, okay? So if you remember how to derive R, khalas, it will be the same, okay? What about this distance from here to here? We call this the phase shift. You see? It's leading or lagging? It's lagging. How much? Psi. This is psi, okay? Starting from this point. This is the phase shift. Okay, this is the phase shift. This is the amplitude. Okay. What about the, what we call this from here to here? We call it what? The period. Do we know the period? We must know the period. Without the period, we cannot draw, right? How much the period? The period depending on what? On the frequency of the oscillation, which is your natural frequency. Okay, the natural frequency. So the period will be equal of 1 over the frequency in hertz, right? Frequency in hertz means what? Cycle per second. So if you change it to omega, the default is radian per second, so it's going to be 2 pi over omega n. You can check the, this is 1 per second or radian per second. Okay, so second will go top, it will be in second. So now this is given. Now you know your period. And these are all the information you need to draw the transient response. Okay, so as you can see, the transient response is similar to the steady state response. It will not change. It will not change. All right, now let's go to the second case. What if we add a damper to the system? See, here is the damping coefficient. Okay, similar to what? Similar to the B or C, the same. Okay, damping coefficient. So when we add a damper, the system will be more complicated now. When I say more complicated, there are more cases. How do I know this? From the solution. Okay, this is the equation of motion in the standard form. This is all given, okay? All right. If you solve for x's after taking the Laplace transform, look at the denominator. What is this denominator? We call it the characteristic equation. We call it the characteristic equation. Why the characteristic equation is very important? And why we call it characteristic equation? Because the roots of the characteristic equation, okay, will show you what kind of transient response you will have. Okay, let me focus on the characteristic equation. This is my characteristic equation again. I want to solve for the roots of the characteristic equation. So if you use math, you can easily get the roots. It's going to be minus 2 zeta omega n plus or minus square root 2 zeta omega n squared minus 4 omega n squared over 2. Or plus or minus omega n outside square root zeta squared minus 1. Okay. Now, clearly, depending on the value of zeta, if you can see from here, depending on the value of zeta, you will have 3 cases. If zeta less than 1, if zeta a small number between 0 and 1, okay, you will have a negative sign under the square root. Okay, and I'm going to call this case underdamped. Why I'm going to call it underdamped? Because zeta is less than 1. What does it mean, zeta less than 1? That means the actual damping is less than the damping ratio. The actual damping less than the critical damping, okay, or your reference damping, okay. So in this case, okay, you will have two complex conjugates. The roots will be two complex conjugates, okay, two complex. This omega d, if you remember omega d from here, it's going to be 1 minus zeta square, which is the same definition that we defined in chapter 3. Case number 2, okay, what if zeta equal to 1? If zeta equal to 1, that means this value here will be 0. That means you will have just one root repeated twice. This two roots are the same and real. Case number 3, I'm going to call it overdamped. Why? Because I'm going to pick a zeta, a number larger than 1. What does it mean larger than 1? That means the actual damping is more than the critical damping. The actual damping is more than the critical damping. I'm going to call it overdamped. Now, if this is a large number, that means what? This is going to be real. So you will have two real roots. I'm going to solve one by one. And I'm going to draw the solution. See what will happen to the solution. So let's start with case number 1. Case number 1, how much zeta, if you remember, underdamped. Zeta here is how much? Zeta is less than 1. Okay, and greater than 0. All right. So if you solve, if you remember, you will have two complex conjugates. If you have two complex conjugates, if you remember from chapter 2, what you're going to do, the next step, you're going to complete the square, right? If you have two complex roots, you're going to complete the square. Once you complete the square, you can go easily to the table and find the inverse. The inverse for this part will be what? Decaying cosine, decaying exponential multiplied by cosine, and this part, decaying exponential multiplied by sine. Sine and cosine, you can take a total r with a common magnitude or amplitude as we did before. Okay? Now let's draw the solution and see what's the difference between this solution and the previous one. This is the time. This is x of t. Okay? What's the difference? Cosine and r similar to the previous solution, but multiplied by decaying exponential. What does it mean, decaying exponential? The amplitude will decay as the time elapses. So starting from here, okay, the magnitude will get less and less and less. Okay? All right. Same analysis, we will have a maximum magnitude. The maximum magnitude will be similar to r. Okay? And this one will be psi, the phase shift from here, from this point. Right? All right. Also, we should know how much this magnitude or the envelope. Let's start with the envelope. Do you know how much this envelope? We should know this envelope. From where we know this envelope? From the decaying exponential. This one. Multiplied by r. So this envelope is r e to the power minus zeta omega n t. Okay. What about this period? We should know the period, otherwise we cannot draw. How much is this period? Yes, the period can be derived from the frequency of the oscillation, okay, which is 2 pi over, what is the frequency here? Omega d, which is given from the solution, okay, and can be easily calculated from the damping ratio and the natural frequency starting from the equation of motion. You don't have to solve it again. Alas, you know, it's going to be always the same. For any underdamped system, it will be exactly the same, just different numbers, r, psi, okay? That's all. How much the period depending on the damping ratio, okay? All right. So this is the transient response for underdamped system, okay? Let's go to the next case. Here, critically damped. What does it mean, critically damped? That means zeta exactly equal to 1. All right. In other words, the damping ratio or the damping coefficient is equal to the critical damping. So if you solve, you will have two repeated real roots. So if you remember from chapter 2, this is going to be power root, a root with a power. Okay, a root with a power means what? It's going to be exponential. It's going to be exponential. Okay, decaying exponential. So if you solve it, it will be very simple. No more oscillation. Okay, no more. There is no sinusoidal, no harmonic motion. Okay, so this is x of t. Look at the solution. So it will start from the initial conditions or initial value, and then it will decay or die as soon as possible. Okay, let me be more clear. This one is exaggeration. It will die very fast. Starting from here, then it will die as soon as possible. Again, it's not very accurate. Okay, exponential decaying. Yes, this one more clear. This is the time. Okay, this is the initial value. Very simple. We call this critical response. Last case, what if zeta here, overdamped, that means zeta is greater than 1. That means the actual damping is larger than the critical damping. That means you will have two real roots. Two real roots means two, if you remember chapter 2, when you want to do the partial fraction expansion, we call this distinctive pool, remember? That means when you solve, instead of one exponential, you will have two exponential. What does it mean, two decaying exponential, not just one? Two decaying exponential means, this is my initial value. That means the response will be slower or faster. It will be much slower. Not just one decaying, two decaying exponential. That means it will be much slower. See? Okay, slow. This is the time. This is x of t. Okay. All right. And these are all the cases that you can see for any second order system. There are no more cases. So any second order system will behave similar to one of these 4 cases. If you have no damping, it will be similar to this one, if you have no damping. If you have a damping, then you check your damping coefficient. If it's underdamped, then this is going to be the transient response. It will be harmonic. And this is the only case, in fact, harmonic motion, when zeta is less than 1. If you have a critical damping, no, it's going to be decaying exponential, similar to first order system. Zeta large, we call this overdamped. No, it's going to be similar to first order system, decaying, but very slow. And that's all. Okay, that's all. These are the cases that you will see. This is a MATLAB solution or MATLAB plot for different cases, similar to what we talked about. So my question, what do you think, which response of these cases is a underdamped system? Underdamped means what? Zeta between 0 and 1. Clearly, it's going to be the red response. Why? Because this is the only response with harmonic motion. Now, if you check the red response, see this one, not the envelope. This is the envelope. No, not the envelope. Check this one. The solid line. Check the damping ratio. How much the damping ratio? So here zeta is what? Less than 1. Underdamped. You see? All right. What about this blue line? What do you think about the blue line? Clearly, this is the critical response. So the damping ratio, see here, it's going to be equal to 1. What about the black lines? Very slow, decaying exponential response. It's going to be larger than overdamped, larger than 1. See, one of them is 2, one of them is 10. Clearly, this one is 10, the slower one. Okay. This is also another demo of a plot of different second order system cases. Okay. My question, what do you think about the red line? Is it underdamped, critically damped, or overdamped? Okay. Now this one, be careful. This one is underdamped. How do I know it's underdamped? If you check the zero line, you see there is a what? There is some amplitude here. Okay, it's very small, but there is amplitude. We call this the overshoot. Okay, so it will pass or cross the zero line. So this is a harmonic motion. The red line is a harmonic motion, but with a very slow frequency or very large period. So if you check the damping ratio, it should be less than 1. See, zeta is less than 1. You see, 0.8. So it's true. This is underdamped. What about the blue one? The blue one is critically damped. And the black lines, which has a very slow response exponential, these are the overdamped system. All right. So we're going to stop here. All right. Because these are the cases, all the cases that you can do or draw for transient response or for second order system. In the next video, we will see how we do the opposite. What if we have experimental response, transient response for second order system, typically harmonic or underdamped, and we want to find the model. Can we do this? This is what we're going to do, inshallah, next class. Thank you very much.